All right, welcome back to the 2011 Cimc. We've almost made it. We're almost out of Part A. We just have one more question standing in our way. That is question number 6, Part A. So let's take a look at it. So the product of all the positive integer divisors of 6 to the power of 16 is equal to 6 to the k for some k. Okay? Determine that value of k. So 6 to the power of 16 is the product of all the integer divisors, the positive integer divisors, is of the form 6 to the something. We just need to figure out that exponent. Okay. So when I start to think about positive integer divisors, my mind always comes back to prime factorizations. I always think that's the best way to figure it out. So why don't we prime factorize 6 to the 16? Okay. 6 to the 16, well, what are the prime factors of 6? 6 is 2 times 3. Okay. So if I wanted to prime factorize it, it would be 2 to the 16 times 3 to the 16. That's what we're looking at. That's the prime factorization. So when we, if we wanted to list out all the integer divisors, this would be the best way of going about doing it. You write it in prime factor form, and then you take all possible combinations of exponents between 0 and the largest exponent there. So if I wanted to, I could write out all the prime factorizations. It would probably take me a while. There's going to be 289 of them. 289 of them. You take the exponents, you add 1 to each of them, and you multiply that. So 16 plus 1 times 16 plus 1, that's 17 squared, 289. So I could write out all 289 of them, but it would probably take the remainder of my time on this contest, and I don't want to do that. So I have to start thinking, well, there's probably a catch. There's probably an easier way to do this. There's probably a formula or a trick or something I'm not seeing. So when in doubt with a question like this, I notice 6 to the 16. The 16 is what's making this unmanageable, what's making this hard, what would make this really long to do by hand. So I have to think that maybe we could try a simpler case. Maybe try 6 to the 1. Write out its prime factors, multiply them. So the positive integer divisors of 6 to the 1 are 1, 2, 3, and 6. 1 times 2 times 3 times 6. Well, that's just going to be 36. That's 6 to the power of 2. Okay. So if they were asking us about 6 to the 1, we'd know that k is 2. But they're not asking us about 6 to the 1. They're asking us about 6 to the 16. So maybe we try a different one. Maybe we try 6 to the 2. Maybe we should even try 6 to the 4. I noticed 6 to the 16. 16 is a square. That might be important in some way. But let's try 6 to the 2. So the factors are, and this is where it gets hard. So we want to make sure we don't miss a factor. So what we do is we sort of make a little chart here. So it has a 2 to the 0, or a 2 to the 1, or a 2 to the 2. It'll go in these respective columns. 3 to the 0, 3 to the 1, 3 to the 2. That way we'll be sure we get every possible factor here. So 3 to the 0, 2 to the 0, that's going to be 1, 2, 4. All the factors of 36 that have just one single 3 as in its prime factorization. 3, 6, 12. And all the ones that have a 9 in their prime factorization. So that's 9, 18, 36. Okay? And if we were to multiply all these together, we'd get 1 times 2 times 4, so that's 8. 3 times 6 times 12. Gosh, that's well, it's just 3 times this top row. So we have 8 times a 3 here, times a 3 here, times a 3 here. So that's going to be 27 times 8. So that's going to be 216, I believe. Yep. And this last one, 9 times 2 times 9 times 4 times 9, so that's 9 times 9 times 9 times 8. So that's going to be, oh geez, 5,832. And we want the product of all these guys, so that's going to be a really big number. 1007769.6. So I'm starting to think that even if I wrote them out, the ones for 6 to the 16 out by hand, that I wouldn't be able to get a good handle on this with my calculator. And out of curiosity, what is that? That's 100777696. That is 6 to the, oh geez, calculator's not cooperating with me. 4, 5, 6, 7, 8. So I think it's 6 to the 8. No, 6 to the 9. Sorry that took me so long. So just with 6 to the 2, we get 6 to the 9. Working on our calculators here. So for 1 we go to 2, for 2 we go to 9. I'm not quite seeing it. But our side calculations here, we had 8, and then we had 3 times 3 times 3 times 8. Then 9 times 9 times 9 times 8. There might be a way to use that. Okay? If we wanted, so we know it's going to be something like 6 to the k, right? And what is the prime factorization of the 6 to the k? Well, it's just 2 to the k times 3 to the k. Okay? So we don't need to figure out the 6 to the k that we get. We just need to count the number of factors of 2 in total, right? Figure out how many 2's are in it. That's going to give us 2 to the k. And we just want 6 to the k. We just want k, really. So, is there a way, looking at this little chart, that I can tell how many factors of 2 there will be? So, none of these numbers contribute a factor of 2. Each of these 3 numbers here, the 2, the 6, the 18, they contribute exactly 1 factor of 2 to the overall product. Each of these guys contributes 4. So 2 to the 2. So these would each add 2 onto k. 1 plus 1 plus 1 plus 2 plus 2 plus 2 is 9. And we got 6 to the 9. So if we wanted to figure out the positive integer divisors of 6 to the 16, we'd draw another chart. So we'd have the 0th column, the 1st column, 2nd column, and so on. There'd be numbers all over the place. And we'd just multiply all the numbers in this sort of square table, and that would give us the 6 to the k that we're looking for. So in the first column, they're just going to be odd numbers. They're going to be 1, then 3, then 9, all the way up to 3 to the 16, which I have no idea what that number is. So the first column, they add nothing to the product, nothing in terms of factors of 2. And if we'd like, we can just count the factors of 2. Now the second column, 2 to the 1, every number in the 2 to the 1 column contributes a factor of 2 to the overall final product. Right? There's one for the 3 to the 0, and a second one for 3 to the 2, all the way up to 3 to the 16. So how many numbers are there from 0 to 16 inclusive? There are 17 numbers. So there will be 17 numbers in this second column, each of them having a single factor of 2. So we get 17 factors of 2. So what is the second column? The third column, the 2 to the 2 column. What does that give us? Each of those numbers will have 2 to the 2 in its prime factorization. So each number, and there are 17 of them, they'll each contribute 2 extra factors of 2 to the overall final product. So the numbers in any generic column, so there will be 17 numbers in every column. In the 2 to the I column, so in the 2 to the I column, each one will have 2 to the I as part of its prime factorization. So each one of them will be giving I factors of 2 to the final product. Columns go up to 16. So this is how many factors of 2 we'll have in the final product. So we can safely say that this number is going to be equal to k. We just need to figure out what this number is. Well, it's 17 times 0 plus 1 plus 2 all the way up to 16. So the sum of the values from 0 to 16, or 1 to 16, however you want to see it. The 0 adds nothing. And if we look back at this contest, at the very start, there's a useful fact. It's helpful to know that if n is a positive integer, then the sum of the n integers from 1 to n is n times n plus 1 over 2. This is a well-known result. It pops up a lot on contests, so it's one you should get used to if you haven't already. So we have 17 times the sum of the numbers from 1 to 16. So that's 16 times 16 plus 1 over 2. Well, what's that value? Okay, is 17 times 16 plus 1, that's also 17 over 2, so that's 8 times 17 squared. And we can punch that in on a calculator, or if you're lucky enough, you can do that in your head. And we get 2,312, or 2,312. And that's our final answer. That's what we would put in the box. And we can make a little note if we wanted to. So all the work we've done, yeah, it was specific to 16, but if you go back, you can easily see how this will generalize for anything, 6 to the n. So it'll be 6 to the n times n plus 1 squared over 2. And if you don't immediately see why that's true, go back and see if you can reason it for yourself. It's fun when you do a question like this, and yeah, you got your specific answer, but you could make a more general result. Okay? And I would challenge those of you who are curious, see why this will work for 10 as well, and see how it would work for any old number. See if you can generalize this for any number with any prime factorization. But if you're not immediately seeing the 6 to the n, and then we get 6 to the n times n plus 1 squared over 2, go back, see if you can work it out for yourself, if you're curious. And if you're not curious, that's okay. We have our final answer. We can move on. This was just a nice little bonus. So we can move on. And in the next three, I think, 1, 2, 3. Next 3 contest question videos, we're going to be dealing with Part B. So we're going to need to do written answers with full justifications. So hopefully you'll join me. Part B, much harder, but sometimes much more fun. And I'll see you guys next time when we continue the 2011 paper.